The first talk today is going to be on transceiver design, and this would be and the speaker today for this particular talk is Dr. Jongwoo Lee. Dr. Lee received his BS degree from Seoul National University in South Korea in 2001, and MS and PhD in EE from the University of Michigan, Ann Arbor in 2004 and 2008, respectively. He was a military officer at the Ministry of Nation Defense, South Korea, for 2.5 years. From 2008 to 2010, he was an analog circuit designer in MmWave Semiconductor Incorporated in Lowell, Massachusetts. He is currently a VP at Samsung Electronics System LSI division. He is leading the IC design team for RFICs, analog IPs, mixed signal circuit design. His research and products include cellular RFICs, Wi-Fi, Bluetooth, RF transceivers, high-speed data converters, low-power PLL SerDes, 5G RFICs, including sub-6 G and millimeter waves, audio codecs, envelope tracking supply modulators, DC-DC power ICs. Dr. Lee has been a TPC member of CICC since 2019 and ASSCC since 2013. So it's a great pleasure to have him on board. And as I proceed, so the way we are going to operate the session today is I will play the video recorded presentation by Dr. Lee and other speakers. And during the course of the presentation, if you have any questions, you can go to the Q&A button on the very bottom, and you can type in your question. At the end of the talk, Dr. Lee and other speakers will be online as well. So once you have typed in the question, I'm going to read that out, and the speaker would be able to respond to your questions. Of course, we are trying it out for the first time as well. This is, I guess, the first major circuits conference which is going virtual. So if there are any glitches, I apologize for that in advance. Hopefully there won't be. If there are any glitches, or if you are not being able to navigate something, just send me or Dr. Wang an email, and we'll take it from there. So without further ado, let's get started with first talk today. And as I mentioned, please make sure to write down your question.
Good morning, everyone.
Q&A.
My name is Jongwoo Lee from Samsung Electronics. Today, I'm going to talk about the fundamentals and challenges about 5G RF transceiver for LTE, new radio, dual connectivity, and millimeter wave. Here's the outline. First, I'll introduce some background about 5G new radio standard. Then I'll focus on frequency range 1, RF transceiver design for ENDC. Frequency range 1 is well known as a sub-6 GNO. And ENDC stands for Ultra NR dual connectivity. E Ultra is LTE and NR is a new radio 5G standard. Frequency range 1 radio system trend and challenges will be followed. Then I will give some examples about the frequency range 1 RF transceiver design for ENDC. Good morning, everyone. My name is Jongwoo Lee from Samsung Electronics. Today, I'm going to talk about the fundamentals and challenges about 5G RF transceiver for LTE, new radio, dual connectivity, and millimeter wave. Here's the outline. First, I'll introduce some background about 5G new radio standard. Then I'll focus on frequency range 1, RF transceiver design for ENDC. Frequency range 1 is well known as a sub-6 GNO. And ENDC stands for Ultra NR dual connectivity. E Ultra is LTE and NR is a new radio 5G standard. Frequency range 1 radio system trend and challenges will be followed. Then I will give some examples about the frequency range 1 RF transceiver design for ENDC. Then topic will be moved to frequency range 2 transceiver design about the millimeter wave. Then I'll say about some motivation about the frequency range 2, why millimeter wave for 5G cellular communication is required. And UE challenges for millimeter wave will be introduced. UE stands for user equipment. It's a handheld device. Then finally, summary will be provided. To carry on the explosion of mobile data traffic, cellular networks have evolved to enhance their capacity. Thanks to carrier aggregation and MIMO techniques, the data rate has been increased annually with LTE standards, release 12, 13, 14. However, the ultra bands are getting saturated, and the needs of higher bandwidth have created the use of above 3 GHz frequency spectrum. Not only the high data throughput, but also the needs of short latency and massive device connections led to new communication standard called 5G and R. The 5G spectrum is classified into two frequency ranges. Frequency range 1 is below 6 GHz, it's a sub-6 GNR, and frequency range 2 is above 6 GHz, called MmWave. The frequency range 1 is defined as standard release 15, and frequency range 2 is defined as standard release 16. There are three major characteristics about the 5G NR. It's eMMB, MMTC, URLLC. eMMB is enhanced mobile broadband, is a very high bandwidth at high frequency, and MMTC is a massive machine type communications, is a massive connections over 1 million devices. URLLC is a ultra reliable and low latency communications for fast communication standard. The spectrum of 5G NR is very wide, even still expanding. In early stage, TDD spectrum and the range of 3.5 GHz to 4.5 GHz are considered. It's a frequency range 1 called sub-6G. It's N78, N77, and N79. And not only the sub-6G, but also mmWave spectrum and LTE refarming bands are considered. The mmWave spectrum is frequency range 2. It's N257, N258, and 260. It's 28 GHz and 26 GHz and 39 GHz. Further, frequency range 1 is no longer sub-6G due to the expansion to the above 6 GHz up to 7.125 GHz. Here's the user requirement for 5G NR. The 5G NR should support the wider bandwidth and higher frequency. For example, for the frequency range 1 requires 100 MHz bandwidth above 3 GHz frequency. And frequency range 2 supports generally 400 MHz bandwidth above 26 GHz. In addition, user requirement should support global roaming. Hence, 5G could be symbiotic relation with legacy protocols. That means the device should provide 5G as well as 2G, 3G, and 4G simultaneously. And demand for small form factor and low power consumption is also important for battery life and battery space. Okay, let's look at some details about the RF transceiver design for ENDC. New radio system trend is no more simple traditional radio. Nowadays is highly sophisticated signal processing based radio. I listed 5 challenges about the RFIC design. First is a wider channel bandwidth, and carrier aggregation and aggregation across route for larger total bandwidth, and higher order MIMO for spectral efficiency increase using more antennas, and higher order modulation for more bits per symbol. and multi-mode operation, including the legacy mode. The first challenge is wider channel bandwidth. There is a comparison between LTA and NR. Pointer. The maximum channel bandwidth of LT1CC is only 20 MHz. And for LT advanced case, it's 40 MHz. For intraband contiguous 2cc CA carrier aggregation case. For single LO, single pass for intraband contiguous CA. And for some application, there can be some 60 MHz intraband contiguous 3cc case, while it's rare. For maximum bandwidth of sub-6G NR, and 1cc is 100 MHz, and 2cc is 200 MHz. So it's at least 2.5 times higher bandwidth compared to LTE Advanced. And also data converter, including ADC and DAC, sampling rate should be much higher. And wideband bandwidth of ABB filter and frequency-dependent IQ mismatch because the channel flatness is necessary. Also, RFIC settling time can be an issue. Let's review the legacy protocols and LTE and NR again. For channel bandwidth of 2G, GSM and GPRS, it's only 200 kHz. So the bandwidth wise, the challenging is in this age, it's only area penalty. And CDMA, the channel bandwidth is 1.23 MHz. And TDS CDMA, 1.28 MHz. And WCDMA, 3.84 MHz. And LT case, there is various channel bandwidth is 1.4, 3 MHz, and 5 MHz, 10 MHz, and 20 MHz. And for single LO intraband contiguous CA case, it's 40 MHz. For TDD and FDD together. For NR case, it's varying from 5 MHz up to 100 MHz for 1cc. And another difference is subcarrier spacing. And subcarrier spacing for LTE is fixed at 15 kHz. But NR case, it's 15, 30, 60 kHz, so it's varying. So especially for 30 and 60 kHz subcarrier spacing case, we need a very fast switching. Here is the plot. Subcarrier spacing of the 15 kHz case, the cyclic fix is 5 microseconds. However, for 30 kHz and 60 kHz, the control interface latency and fast analog settling time is required because the cyclic fix is getting shorter. Second challenge is carrier aggregation and aggregation over RAD. RAD is radio access technology. And LTA is a conventional CA case. Now, let me use laser pointer here. Okay, there are three cases: interband CA, intraband contiguous CA, intraband non-contiguous CA. Interband CA, in this case, carrier components assigned at a different frequency band. For example, in this case, CC0 is assigned frequency band A, CC1 is assigned frequency band B. And intraband contiguous CA, the frequency band A contains all the carrier components, CC0 and CC1. However, it's contiguous. So in this case, we can use a single pass to deal with all of these components. For intraband non-contiguous CA case, it's similar to intraband contiguous C, but there is a space and distance between CC0 and CC1. And all the CA cases combine configuration based on the service operator's spectrum holding. On the other hand, ENDC, so ultra energy connectivity case, not like LTA, all the different route can be assigned for all the CC case. So in this case, LTE intraband contiguous CA plus interband contiguous CA plus NR non-contiguous intraband CA plus interband carrier aggregation. So the combination is quite complex. So there is an example in SKT in Korea. It's a band 1 plus, it's a 4x4 MIMO, band 3, band 5, band 7, and band 7 plus N78 or N77. So in this case, we have to take care of a lot of combination over route. The third challenge is higher order MIMO. The basic LTE UE device requires only 2x2 MIMO. It's a combination of primary path and diversity path. However, multiple independent LTE NR data stream at the same frequency channel requires the higher order MIMO. And high-end LTE NR UE device requires 4x4 MIMO. And the future, maybe 8x8 MIMO can be considered. And data rate increased by 2 times per 2 times increase in number of N. So each increase in square level. High order MIMO is very attractive to the service operator for the higher throughput, but there is no free lunch. It requires the higher number of antenna, and we cannot meet the small form factor. And the RF front end, the bill of material number can be increased, and number of RF receiver paths increased too. There are multiple sub-filter and external LNA, and PCB area and bunkers will be increased very high. And multiple input port and receiver paths, LNA to ADC, will be increased, and RXLO distribution will be very complex for design. The fourth challenge is higher order modulation. From QPSK up to 256 or 1024 COM, the increased number of bits per symbol is main feature. Okay, let's look at the table. Okay, for QPSK, the bits per symbol is only 2, and 16 COM case, each bits per symbol is 4, and 64 COM, and it's a 6, and 256 COM is 8, and 1024 COM is 10. That means reference to QPS case, the scaling factor is 1, and for 16 COM the scaling factor is 2, and scaling factor for 16 COM is 3, and scaling factor for 256 COM is 4, and 1024 COM is 5, and data rate in megabps is 20 MHz bandwidth rank 4 case, it's rank 4 MIMO. QPS case is 100 Mbps, and 16 COM is 200 Mbps, and 54 COM is 300 Mbps, and 256 COM is 400 Mbps. 1024 COM is 500 Mbps. It's quite straightforward and proportional. However, the required SNL is getting higher for 256 QAM is minus 35 dB SNR, and 1024 QAM is minus. For practically, we need more sometimes. So that means we need more ADC SNR in NR, even for wide bandwidth, and low noise and high linearity from RF to baseband is required. And to achieve this required SNR, a very good integrated phase noise in LO is necessary. Also, low IQ mismatch is required, especially because it's wideband, frequency-dependent IQ mismatch calibration for wideband. The final challenge is multi-mode operation, including the legacy mode. If we design the RF transceiver in single chip, we have to meet all the requirements and challenges about the legacy protocols and new radio. For example, for 2G, the RF sensitivity is very challenging, down to minus 110 dBm. The limit is by 1 of F noise, so we have to increase the size of transimpedance amplifier. For the transmitter side, the output RF spectrum is very strict. For 3G and 4G, the FDD case, the TX leakage separation with IIP2 calibration is very important, and inner loop power controller should be included. For LTE advanced case, the carrier aggregation and simultaneously operate multiband C coupling, the RF coupling issue, and especially for CIM3 for 1RB case, it's a very dense power transmission case, the sparse emission can be very challenging. And for sub-6 GNR, the wider RF bandwidth up to 100 MHz at higher frequency channel is also challenges. Now let's turn to the topic of how to build the RF transceiver design for ENDC from architecture level. Now let's turn to the topic of more details of design consideration for ENDC. From now, I will use some laser pointer. First of all, the feature-wise architecture should be considered due to band combination complexity and enhanced performance. A higher-order carrier aggregation and MIMO example will be introduced. Due to LTE-NR dual connectivity, there is a coexistence problem that should be solved. The number of data paths should be increased, and still RFIC should keep small form factor. Unwanted RF coupling issue is getting worse. Especially, the number of downlink paths is increased a lot, up to 18 paths. Sometimes it can be more. The band combination is quite complex, more than tens of thousands combination. That's an issue. The circuit size reduction should be followed to keep the small form factor. So area efficient architecture is necessary. 100 MHz channel bandwidth is another big challenge. Also, 100 MHz envelope tracking technique almost hit the limit of analog-based supply modulator. The increased the uplink throughput, 256 QAM is required for better UVM. So phase noise requirement is so tight. For FDD system, TX leakage is causing IIP2 issue, since just device matching cannot be guaranteed for mass production. For the feature-wise architecture, the partitioning between link bridges should be carefully considered between front-end module and RF transceiver. These days, LNA PA module with integrated duplexer is widely used, it's LPAMID, for the front-end module. If LNA is integrated inside the front-end module, we can achieve better sensitivity that relax the noise figure burden of our transceiver. However, the linearity burden will be increased with higher TX leakage, which requires IIP2 performance better than 70 dBm and IIP2 performance better than 0 dBm. The external LNA should be wideband to cover all the non-CA band group. Which makes it impossible to use post-SAW filter. Also, RFIC internal LNA should be wideband, and integrated on-chip matching is preferable. For wideband up to 100 MHz and MIMO 4RX, here, transmitter and receiver analog baseband filter bandwidth should be increased more than 2.5 times wider than LT advanced case. In addition, data converters, including ADC and DAC, sampling rate should be increased proportionally. Since the band combination increased a lot, the band-dependent RF port and LO interface design get high-order carrier aggregation in MIMO is one of the main features in ENDC. Here's an example of possible ENDC phone design combination. SKT operator case in South Korea requires a CA combination of band 1, band 3, and band 5, and band 7 and 7, and NR bands 78 or 77. Band 1 is 2.1 GHz frequency band, which is classified to mid-high band. Band 3 is a 1.8 GHz frequency band, which is classified to mid-band. Band 5 is 850 MHz frequency band, which is classified to low band. Band 7 is 2.6 GHz frequency band, which is classified to high band. And 77 is 3.7 GHz frequency band, and 78 is 3.5 GHz frequency band. Both are UHB or NR bands. So it's here. In this case, 8 antenna and 4 here, required for this combination and antenna diversity. To support this band combination, at least 18 receiver paths are required. And LO distribution is quite complex. And wideband antennas are required to share each band group. In front end, many diplexer to connect multiple band group carrier components to the wideband antenna. Also, in front end, wideband LNA front-end module, or a wideband LNA PA module with integrator diplexer are required. As shown in a previous slide, the frequency band combination is complex. It causes coexistence problem between other frequency band group, especially LT band 3 and NR band N78. In this case, has a serious coexistence issue. LT band 3 is 1.8 GHz frequency, and the band 3 transmitter second harmonic signals, it's directly falls into N78 receiver band, which ranges from 3.3 to 3.8 GHz. 3GPP already defined the maximum sensitivity degradation based on ENDC band combination about those harmonic exceptions for the downlink band. Another consideration is intermodulation between two uplink signals, such as LT transmitter and NR transmitter. For example, intermodulation between LT band 3, TX, and NR band falls into LT band 3, RX. To alleviate the coexistence case due to harmonic or intermodulation, careful flow planning and port configuration are necessary. About the coexistence case, there are a lot of RF coupling paths inside RF transceivers. Thus, multiband carrier aggregation coupling degrades SNR, and it affects throughput performance. There are four major case coupling paths of the RF couplings. Case 1 is transmitter output harmonics are coupled to receiver input. It's case 1. Transmitter RF here is harmonic is coupled to RF receiver RX band. And case 2, it's a transmitter RF harmonics coupled into receiver or transmitter DCO. It's a digitally controlled oscillator. In case 3, receiver or transmitter DCO here is a coupled to, in case 3 here, it's a coupled to the RX input. And final case, the cross-coupling occurs between other DCOs. Above all, careful flow planning is required for port-to-port and ball-to-ball isolation, or DCO to DCO, cross-coupling alleviation, and LO to LNA mixer input isolation. And here, programmable LO divider would be another option to avoid case 3 or case 4. For ENDC, complex carrier aggregation operation scenario is another big constraint for RF design. The first consideration is how to assign receiver path for primary cell and secondary cell as carrier components number increases. Generally, it is preferred to maintain the link using the same primary cell at any CA and MIMO case. To reduce the power consumption, a single wideband path is preferred than multiple narrowband paths for intraband CA case. Second consideration is how to assign a receiver transmitter local oscillator to receive receiver and transmitter path for FDD and TDD joint CA case. Third consideration is how to assign supporting band combination at each receiver path and corresponding receiver LO. In addition, we need to consider how to determine the number of receiver ports per supporting band and front-end configuration. Then, how to realize the systematic receiver operation scenario should be considered. Finally, legacy mode compliance with LTA and NR should be considered. Here is the intraband CA operation scenario. The LNA should have a functionality of splitting to different mixers as shown in mixer 1 and mixer 2. The wideband LNA here, input impedance should be constant to guarantee a good gain and sensitivity. Also, independent gain control is required regardless of CICC count. Finally, careful flow plan and layout are required for the isolation from RF coupling between other CCs. So, yeah, coupling between this. Carrier aggregation receiver has multiple receiver paths. The transformer balun at mixer input takes large space in the receiver. The connection between RX input port to mixer should be increased for CA4RX supporting capability. And it increases the number of sub-LNA and massive RF routing. A good example to reduce the receiver size is a switchable transformer balun to cover low band to high band. It makes scenario-based LNA to mixer connection. 100 channel bandwidth support is another big design challenge. Not only receiver analog baseband filter bandwidth increased to 100 MHz, but also transmitter analog baseband filter bandwidth should be increased. Even for DPD support, a single-side baseband bandwidth should be more than 125 MHz. Due to bandwidth expansion and image tone rejection, the sampling rate should be very high. Also, the channel flatness is required. Let's see the laser point again. Okay. The 100 MHz transmitter bandwidth makes technical difficulty for design of envelope tracking supply modulator. The ET modulator should implement wideband linear amplifier, support NR 100 MHz envelope tracking with high reliable process technology. For example, power management IC technology to endure high voltage. Now let's look at this block diagram. So supply modulator itself should be designed to support 100 MHz envelope tracking. It's a big challenge. Also, NR PAMID design should have flat in-band gain variation. So new radio PA module integrated duplexer. The PA here, the in-band gain variation control is very important. Also, the NR PAMID design with very small decoupling capacitance at supply node is required. Generally, less than 200 picofarad is necessary, because if there is more than this number of capacitance, it will be limited by this parasitic. The bandwidth will be limited, so it will distort the envelope signal. Also, the parasitic PCB inductance from SM output, supply modulator output, to PAMID is very, very important, because this form the channel bandwidth limit, the supply bandwidth limit, and also the control of PCB routing in the capacitance of this line is also very important. Parasitic PCB capacitance should be less than 5 picofarad generally, because if it exceeds this number, the ET DAC bandwidth can be limited, so envelope signal is limited by this arch constants. Also, memory DPD should be implemented in Omlink 256 QAM modulation is required to increase throughput with better EVM. For 256 QAM spec, less than 3.5% EVM is required. It's just 3 GPP spec. But for the real implementation in UE, operator requires better than 2.5%. With some margin, 2% EVM is required. To achieve the 2% EVM, frequency-dependent IQ calibration, FDIQ, is highly crucial factor. For FDD system, TX leakage is causing IIP2 issue. So TX is very high power. So through here, it falls into the receiver band in FDD system is operating simultaneously. So mismatch of mixer and here are causing the IIP2 issue. Since the device matching cannot be guaranteed for mass production, calibration is required. To reduce the manufacturing cost with external equipment calibration, some internal calibration hardware for like our internal loop back path would be a big help. A dedicated feedback receiver path is used for IP2 calibration, and here can be many calibration algorithms to find the sweet spot. Here's an example. It's a 4-point fast calibration sweep. Here's an example of the FR1 RF transceiver design for ENDC. It is a single-chip CMOS RFIC for sub-6G new radio supporting also all the legacy 6 modes. The supporting frequency bands are from 600 MHz to 6 GHz to cover all the legacy bands and UHB NR bands. There are 7 downlink paths, including UHB and LLA bands, and the 7 primary paths and the 7 diversity paths are identical. It supports multiple carrier aggregation, including inter- and intraband CA and 4x4 MIMO. The max data throughput is above 3.15 Gbps for downlink and above 1.2 Gbps for uplink. In order to use with the wideband front-end module such as LPAMID, the wideband LNA is designed for various CA combinations. For various CA combinations, each LNA has multiple output connections to each down conversion path. It employed current mode passive mixer with 25% LO for low mid high bands and 50% LO for UHB NR bands. To support sub-6G new radio, analog channel based bandwidth can be extended up to 100 MHz. To reduce the size of the receivers, a bandwidth configurable transformer balun is proposed. To support downlink 1024 QAM modulation, low noise receiver analog baseband filter, good integrated phase noise in receiver LO, small IQ mismatch, and higher SNDR ADC design are implemented. Here are some measurement plots from receiver side. Let's use the laser pointer again. Here. Okay. The peak CINL, the channel to interference from noise ratio, is around 36 dB for LTE band 10. All the bandwidth is LTE 10 MHz case, band 1, and band 2, band 3, band 5, band 7, band 8 case. All the plots are similar curve, and the sensitivity level is around minus 100 dBm over many
frequency bands: band 12, band 17, band 20, band 5, band 8, band 3, band 2, band 1 and 4, and band 7. The LT EVM and NR EVM case are measured. It's a 64 com case, 8 by 8, and 256 com for NR case, 1616 EVM constellation plot, and that's a spectrum for LT, band 1, 20 MHz, and NR 78, NR 40 MHz. At this time, there is some equipment limit to measure up to 100 MHz. So, band 1, LT 20 MHz, 64 com case, EVM is measured 2.1% before IQ calibration. And for NR N78, NR 40 MHz, 256 com case, the EVM is measured at 1.8%, also before IQ calibration. Actually, the initial power consumption of one CALT is 18 milliamps, which measured, but after some tuning. Now, the two cases of transmitter performance measure are shown here: 40 MHz LT and 100 MHz NR. Point again. Okay. 40 MHz LT and 100 MHz NR here. And here's a LT 40 MHz case spectrum and transmitter constellation plot here. And for NRLT, 100 MHz spectrum is shown here. And 256 QAM case, the constellation plot is here. The measured ACLR, adjusted channel leakage ratio, is better than minus 41 dBc, and EVM does not exceed 2% at the highest output power. In this case, the CC0 EVM is only 1.12%, and CC1 EVM is only 1.35% for 64 COM 2TX case. For NR case, also EVM does not exceed 2%. 256 QAM EVM is 1.94%. The power consumption of transmitter was also measured, but this is before tuning, so it's early stage measure.
Then let's move to the frequency range 2 transceiver design, starting from the mmWave motivation. By Shannon theorem, the channel capacity can be increased by wider bandwidth and higher SNR. Thanks to carrier aggregation and higher order modulation scheme, the data throughput gets increased annually. However, the practical spectral efficiency limits are being reached in frequency range 1. Now, mmWave area is the only frequency band to support wider bandwidth with fixed fractional bandwidth. Of course, there are many limitations and challenges with mmWave design. Due to small form factor, the transmission power is limited, and due to high path loss and high straightness in error provide a big practical limit. Multiple antenna array and beamforming technique could overcome those limitations respectively. Also, process technology should be a bottleneck due to Fmax, Ft, skin effect, and supply limit. High order modulation and millimeter wave is challenged since it is not easy to achieve good integrated phase noise.
Antenna array is a key factor of millimeter wave design. Okay, point option. As the number of array increases, the main lobe is getting narrower. For example, this case. Let's look at this case. The distance of array is fixed to 0.5 lambda. So if number of array case 2 here, there is only 2 lobes for green, here and here. Then number of 4 cases, the main lobes here in blue color here, and only 2 main lobes and 4 side lobes. In this case, much narrow, and number of n is 8 cases. The red line is much narrow. So as n increases, it's getting sharper. And let's look at the distance between arrays. So let's fix the number of array to 4. So yeah, let's compare to this. And the distance is fixed of 0.5 lambda case. It's same with this blue line. So it's 2 main lobe and 4 side lobe. If the distance is getting larger, like 1 lambda case in red line, more side lobes in one period. So in this case, the side lobe is very higher, so energy is side lobe is larger. And even for distance of 1.5 lambda case, it's green here. So it's main lobe, and there are so many side lobes here, and big 4 side lobes. So to avoid any grating lobe, the largest spacing between the elements should be less than half wavelengths. So less than 0.5.
There can be many configurations for the trade-off of antenna array. Antenna array can affect the UE from form factor, beam management, and out power of power amp. Okay. Let's see this example. We have 3 examples of the antenna array. It's 1x4 cases, 2x2 case, 4x4 case. Let's define the spacing is D. The bandwidth and the carrier frequency almost match together. In this case, if the spacing is 4 millimeter, 1x4 case, the antenna gain is 9.72 dBi, and spacing of 8 millimeter case is 12.37 dBi. And 2x2 case, the antenna gain is almost similar, and 4x4 case, antenna gain is much higher. And yeah, 4 millimeter dimension case, it's almost 5 dB higher, and 8 millimeter case, it's almost 7 dB higher. Beam radiation pattern for 1x4 looks like this. It's antenna array is here, and beam pattern is here. And 2x2 case, it's very straightforward to the beam pattern. And 4x4 case, it's sharper beam arrangement.
And requirement of power of the PA 1/4 case, it's 14.3 dBm for all the same EIRP for spacing 4 mm and spacing 11mm, 11.6 dBm. And 2/2 case, each PA is for 4 mm case, 14.8 dBm, 8 mm case, 11.2 dBm. However, 4/4 case, of course, the number of array is 4 times larger. So each PA output is only 3.4 dBm for 4 mm spacing and minus 1.3 dBm for 8 mm spacing case. All of this design have issue, especially related to form factor. The total size is an issue. And while the antenna gain and each required power of the PA is less at the 4/4 case, the total size is much larger. So at least twice or 3 times larger. And all this configuration has side load.
By controlling the progressive phase difference between the elements, the maximum radiation can be squinted in any desired direction to form a scanning array. There are 2 options for phase array architecture for beamforming. The first one is LO phase shifting and the second one is RF phase shifting. For LO phase shifting, the gain is constant over phase code and we can achieve high phase resolution. However, it consumes very high power due to heavy LO distribution. Also, mixer conversion loss in signal chain is another penalty. On the other hand, RF phase shifting architecture is simpler about mixer and LO distribution. However, amplitude variation over phase code is a bottleneck and additional phase shifter in signal path causes signal loss.
For the RF phase shifting architecture, passive design and active design are possible. And passive design is implemented with cascaded phase shifters with LC components. Here is an example, like here. Okay. Due to passive design, it's only LC, basically. Theoretically, a very low power consumption can be achieved. That's pros and cons. It's a higher resolution requires more stage and higher loss and SNR trade-off and die size. Let's look at here. In this case, to achieve 11.25 degree resolution, we need 180 degree shifter, 90 degree shifter, 45 degree shifter, 22.5 degree shifter, 11.25 degree shifter, at least 5 cascaded stage. Because there is a path loss, we need to amplify the signal to guarantee the SNR, so there is additional LNA. On the other hand, for transmitter side, if we achieve, implemented 5 stages of this passive phase shifter, we need to drive this phase shifter with more current, and so that means it's not low power. So there is a drawback because of this path loss, and the resolution is very limited. Also, the area can be very large. So if we want to increase the resolution, we need more stage. So that's drawback of passive design.
Not like passive shifter, active design uses IQ generation and vector sum method. The active phase shifter can provide additional gain in signal path with higher resolution and small die size, but it increases active power consumption. Unlike base station development, user equipment has more challenges for millimeter RF design. Here is the list for UE challenges for millimeter wave. Due to phase noise and IQ mismatch limitation, obtaining good SNR at millimeter wave frequency for higher modulation downlink is difficult. Generally, UE capability is limited by uplink. Millimeter wave CMOS PA P1 dB efficiency and thermal issues limit the TXEIRP, its equivalent or effective isotopically radiated power. Form factor limit in UE is a major challenge. Antenna module size is limited inside handheld device such as smartphone. Hence, the number of antenna and IC die size are limited. To support up to 400 MHz channel bandwidth per CC and interband CA configuration over 1 GHz is really wideband signal path. Not easy to implement with low power. Antenna module placement and interface inside UE impact architecture choice. Here is the key specification comparison between frequency range 1 and frequency range 2. About the mode, frequency range 1 should support both FDD and TDD, while millimeter wave needs to support only TDD mode. Hence, FR2 has relaxed transmitter noise floor and receiver distance requirement. About the TDD, FR2 has faster mode transition. About the transmitter characteristics, FR1 output power range is from minus 50 dBm up to 27 dBm with better than 3.5% EVM to support 256 QAM modulation. However, FR2 requirement is a bit relaxed. In FR2 case, we consider EIRP since the transmit power is beamforming phase array. The EIRP target is from minus 13 dBm to about 22 dBm with less than 8% EVM to support 64 QAM. Since FR2 SNR is difficult to achieve at very high frequency and large bandwidth, the modulation scheme is stayed at 64 QAM. For receiver characteristics, sub-6 GNR reference sensitivity target is better than minus 95.3 dBm for N77 10 MHz case with minus 25 dBm max power. However, FR2 noise floor is much relaxed due to array. The FR2 reference sensitivity target is better than minus 88.3 dBm at N257 band 50 MHz bandwidth with a max power of minus 25 dBm. FR2 adjacent channel selectivity blocking spec is also relaxed. FR2 ACX1 blocking spec is only 23 dB, while FR1 ACS1 blocking spec is 33 dB. However, FR2 channel bandwidth is wider than FR1. While FR1 bandwidth ranges from 200 kHz up to 100 MHz to cover 2G, 3G, 4G, and sub-6 GNR, FR2 bandwidth ranges from 50 MHz to 400 MHz. Considering intraband CA case, FR2 integrated bandwidth can be expanded more than 2 GHz. Here's an example of frequency range 2 with transceiver architecture. Two data streams are needed for dual polarization antenna to support rank 2 MIMO or diversity gain. It's a horizontal pole.
and vertical polarization here, and trade-off between number of elements in the antenna array and form factor. In this case, the number of elements is 4. 1, 2, 3, 4. And for horizontal pole is 4 channels, and vertical pole there is 4 channels. However, if the number of channels increases, we can get more antenna gain, and each required PI output can be relaxed. So there are many positive sides. However, the form factor can be worse. So integrated transmitter receiver switch interface patch or dipole antenna needed. Also there is an interface, and so there are a patch or dipole antenna module should be connected through this switch. Also, large signal bandwidth support is needed in baseband low-pass filter, ADC, and DAC. So generally, the baseband low-pass filter bandwidth is 400 MHz, and the IQ, ADC, and DAC sampling rate should be more than 1 GHz per second, generally. And there should support multiple modules to cover many directions. So generally 3 or 4 modules.
About the block level design challenge, the first difficulty is tough phase noise requirement for mmWave. For same bit error rate and symbol rate, lower EBM is needed for higher order QAM. To meet the spec of 64 QAM modulation and 8% EBM, single-side band integrated phase noise spec is about -33 dBc. This number is much relaxed compared to 256 QAM case, which requires -40 dBc SSB integrated phase noise spec. However, this -33 dBc IPN spec is translated to 126 femtosecond RMS jitter at 48 GHz, while 840 femtosecond RMS jitter at 6 GHz. This means the FR2 PLL jitter noise should be about 7 times better than FR1 case. Even compared to 256 QAM FR1 case, the 64 QAM FR2 RMS jitter should be about 3 times better. About the circuit impairments, AM compression can be corrected with analog or digital pre-distortion, and AM/PM compression, IQ mismatch, and gain variation can be corrected with calibration and equalization. However, error phase noise cannot be pre-distorted or equalized. To support mmWave frequency, large PLL divider ratio is required, and possibly larger loop bandwidth makes the reference clock quality more critical. For example, using 52 MHz TCXO as a reference clock, at 6 GHz, the divider ratio is only 41 dB, while at 40 GHz, the divider ratio is 58 dB. That means 17 dB higher crystal oscillator noise is amplified at carrier frequency. There are some possible solutions. First, increasing the reference clock frequency. However, crystal technology has a frequency limitation related to standby power and form factor for handset platform. In addition, the reference clock should be shared with GNSS and FR1 cellular system. Low phase noise PLL architecture is necessary to minimize additional in-band noise contribution from PLL circuit itself. Low phase noise VCO is also important. Then, we can reduce the PLL loop bandwidth to low-pass filtering the reference clock noise.
About the transmitter side, CMOS PA linearity and efficiency are the major challenges. The CMOS PA efficiency is limited by supply voltage or device stacking. To improve the PA efficiency, some new research should be investigated. Advanced supply switch or envelope tracking technique can help. But large bandwidth support is technical bottleneck. Digital pre-distortion can improve the linearity, but calibration and feedback path at millimeter frequency is difficult yet. Dual T-power amplifier can be considered as used in base station. However, die size and broadband support can be a limitation for UE application. Here is an example of FR2 transmitter architecture. 4 transmit elements per polarization are implemented. So number of elements is 4. So number of elements is 4 here. 0, 1, 2, 3, and receiver side 0, 1, 2, 3. So all the elements are 4. And the saturation power is 14 dBm. And because the number of elements is 4, the array gain is 12. So it's 20 log n. And antenna gain is 4 dB by design. And front-end loss is assumed minus 3 dB based on routing and case loss. And back-off DFT or FDM, we assume minus 3 dB. However, the back-off requirement depends on modulation scheme. So in this case, TX-EIRP is 24. So 14 plus 12 plus 4 minus 3, then 24. And based on region dependent, the emission is like here. And also we need to consider multi-band antenna interface. And also again, it's a trade-off between power consumption and form factor. Receiver design challenge is mainly about intra-band carrier aggregation. Carriers have fragmented frequency bands within N260, which is 39 GHz band. Okay, so for N260 case, the CC0 is here, CC1 is here, CC2, CC3, CC4. Only 200 MHz bandwidth for each carrier components, but all the aggregated bandwidth is up to 2 GHz. So in also spec-wise, 3GPP support intra-band non-contiguous CA up to 2.4 GHz total aggregated bandwidth. So above example shows the 5 CC case within 2 GHz. And millimeter phase array at 37 to 40 GHz can receive 2 GHz with good band length. However, if it's handled by single LO, baseband circuits and ATC is very challenging. They need more than 1 GHz analog bandwidth, so it requires very high power consumption, and there can be some mismatch issue. So it may not be. To alleviate the analog bandwidth burden, we can use multiple LO signals to break down to multiple LO bandwidths. In this case, we can break it down into 2 smaller bandwidth. Each baseband path handles less than 1 GHz bandwidth. Still 1 GHz bandwidth is challenging, but better than 2.4. And in this case, the single sideband bandwidth is only 500 megahertz. So ADC, DAC, ADC and analog baseband filter bandwidth can be less than 500 megahertz. So it's doable. However, it's still challenging to maintain flat frequency bandwidth, flat frequency response through millimeter wave. About UE implementation, antenna module and RFIC placement should be considered carefully. First of all, millimeter wave antenna and phase array chip, including PA, LNA, phase shifter, need to be placed near device edge. And antenna and phase array chip placed in module together to reduce any loss in electromagnetic impact. And multiple antenna modules should be used for better spherical coverage. In this example, there are 3. 1, 2, 3. Also, there can be patch antenna for this direction and dipole antenna for this direction here, and also dipole antenna for this direction here, and dipole antenna for this direction here. And we need to consider carefully about the partition of the phase array RFIC and interface to modem chip here. That's the one of final design consideration is the interface between phased array RFIC and modem. The number of interface signals to antenna module should be minimized due to long routing loss and form factor. One of the ideas to reduce the interface line is embedding reference clock and control signals within the signal lines. Now, I'd like to wrap up my presentation. About 5G RF transceiver design, wider bandwidth, and more sophisticated techniques are introduced for gigabit class performance. That includes carrier aggregation for wider RF bandwidth and aggregation across diverse spectrum such as ENDC, and high-order MIMO support for better SNR, and higher-order modulation for more data density. About the frequency range 2 UE RF design, still main challenges remained. PLL phase noise is critical for obtaining good SNR at millimeter wave. For uplink transmission, millimeter wave CMOS PA power and efficiency have trade-off with module size. Wideband receiver, intraband CA makes complicated receiver architecture. And antenna module placement and form factor impact the architecture and interface decision. Above all, power, performance, and area is the key factors for the success of RFIC design. Thank you so much for sharing your time here.